Now let's talk about the properties of stars. How can we understand them overall? This work started in the 19th century with some very important astronomers who were doing taxonomy of stars. At that point, we didn't understand how the stars work, and so these were people who were looking at stars and their properties, and in particular using the tool of spectroscopy, taking spectra of the stars, looking at the distribution of colors in fine detail. The early figures here are Mary Draper and Henry Draper. They were wealthy amateur astronomers working in Boston at the Harvard College Observatory. They were pioneers of astrophotography, especially of taking photographic spectra. After her husband died, Mary donated their equipment to the Harvard College Observatory and endowed a research fund for the work on stellar spectroscopy. The man who orchestrated this business was Edward Pickering, who was trained as a physicist at Harvard and taught at MIT. He became the director of the Harvard College Observatory in 1877, and he pioneered the technique of stellar photographic spectroscopy. He also invented the mechanism of putting an objective prism in front of a telescope so that you could take the spectra simultaneously of hundreds of stars on large photographic plates. In the Harvard College Observatory, over a period of years, they accumulated a massive collection of stellar spectra on photographic plates, and Pickering needed help to digest and sort this huge pile of data. So he hired the computers. They were called the computers in part, and they were women because a woman, Mary Draper, donated the research funds, and in part because women could be hired at lower wages than men. They were paid barely 50 cents an hour after they'd been doing the job for a while, and they were often willing to work almost for free to break into the field. Pickering began hiring women computers to do this work. It was painstaking, tedious, tiresome work, incredibly detail-minded. The orchestrator of this effort was Wilhelmina Fleming, a Scottish teacher who had emigrated to the United States. Her husband died soon after, leaving her to raise their son. She started with work as a maid for the Pickerings and then was hired by Harvard College Observatory as one of the first computers. But she quickly learned science and devised a stellar classification scheme based on the strength of hydrogen lines in the spectra. And she is known to be the person who discovered the first white dwarf star. In 1898, she was appointed curator of astronomical photographs at the Harvard College Observatory. And then we come to two pivotal figures in the history of astronomy, also women that were far ahead of her at their time because women did not have faculty positions at any major university in science at this time. Annie Jump Cannon attended Wellesley College and studied physics and math and became a noted photographer. She was deaf due to a bad case of scarlet fever, and she enrolled in Radcliffe as a special student, and hired by Pickering, she improved Fleming's classification scheme. She created the OBAFGKM stellar classification scheme that astronomers still use, and she, in her career, classified more than 350,000 stars from photographic plates, a prodigious amount of work. It's hard for me to imagine. The Henry Draper catalog gave 225,000 of these stellar classifications down to 10th magnitude. She worked with Celia Payne, another major figure at the Harvard College Observatory, to deduce that the stars were made mostly of hydrogen and helium, the first time we ever knew what the stars were made of. At the same time, Henrietta Swan Leavitt attended Oberlin College and also graduated from Radcliffe and was hired by Pickering. Like Cannon, and for the same reason, she was also deaf. She worked on photometric catalogs, especially of the Magellanic Clouds, and she discovered over 1,000 variable stars in the small and large Magellanic Clouds. The period luminosity relation she discovered for these so-called Cepheid variables would become crucial in measuring the distance to galaxies. And this work has gone into popular culture. Davis Sobel wrote a beautiful book called The Glass Universe about the ladies of the Harvard Observatory and how they took the measure of the stars early in this century. This work has also gone into more than one play, which are now doing national tours, about the women at the Harvard College Observatory, who really basically ran their own shop and did some of the foundational work on stellar spectroscopy early in the last century. Another major figure was Cecilia Payne-Gaposchkin. She'd been urged by Gustav Holst to study music, and she had great talent in that area. Instead, she chose to study physics and chemistry at Cambridge in England. but she turned to astronomy after being inspired by a lecture by Arthur Eddington talking about his eclipse expedition that confirmed general relativity. She was not awarded a degree at Cambridge. Women did not receive degrees there until after the Second World War. But she'd met Harlow Shapley at Harvard College Observatory, who just started a graduate program. Luckily, she got a fellowship to enable her to study there because she had no means to pay for the education. In 1925, she became the first woman to receive an astronomy PhD from Harvard, Radcliffe College. And in 1956, she became the first woman to be appointed full professor at Harvard, and then the first chair of the astronomy department. She was a true pioneer and pathbreaker. A lot of work was done also on an object of great interest in astronomy, the Hertzsprung-Russell diagram, which is how we classify stars, by two astronomers who collaborated and also worked independently. N.J.R. Hertzsprung was a Danish physicist and astronomer who started in chemical engineering and came to astronomy through his love of photography. He invented the idea of spectroscopic parallax, using the line widths in stars to predict their luminosity. And he created the first HR diagram, which is a plot of spectral type or temperature against luminosity for the Pleiades. Henry Norris Russell got his degrees from Princeton, and he worked on stellar parallax. He also had correlated stellar magnitude or luminosity with spectral type, and he found the same behavior in the same diagram as Hertzsprung, so they worked on this together. He deduced that stars evolved by changing their chemical interpretation, and this is foundational to understanding stellar evolution. On the left, we see the very first HR diagram, which shows a correlation between luminosity rising to the top of the diagram into the left corner and temperature, cooler to the right and redder to the right and hotter or bluer to the left. A more modern version of the HR diagram is on the right side. The theory of this stellar structure and how stars evolve and operate really came from one man, Arthur Stanley Eddington, a prodigious writer and scholar, an astronomer, a physicist, and a mathematician. He was the Plumian professor at Cambridge. He was also a science celebrity of the time and wrote books that were popular in common language so that everyone could understand the story of the stars. His most influential book was in 1926, The Internal Constitution of the Stars. Eddington was supremely confident in the power of scientific inference. He made an extraordinary claim in one of his books. He said that had humans lived on a cloud-shrouded planet with no visible night sky, we would have been able to use the laws of physics to predict that stars existed and what their properties were. I'm not quite sure he was right in being that confident. He was also self-confident. A story is told of him when he was asked in 1919 if it was true that only 3 people in the world understood general relativity. He replied, "Who's the third?" Let's look at an overview of stellar properties. All stars are really doing the same thing. They're fusing lighter into heavier elements. What elements they fuse and the temperature and pressures they do it at depends on their mass. If we look at stellar properties, we see a range of brightness, intrinsic brightness, that is enormous. It goes from stars that are 10,000 times less luminous than the sun to stars that are 10 million times more luminous than the sun. The temperature range is not as severe. The sun has a surface temperature of about 5,600 Kelvin. Stars go as cool as 3,000 and as hot as 50,000. We can measure the range of star masses by using binary star orbits and Kepler's laws. The lowest mass stars are about 8% of the mass of the sun, and the heaviest about 100 times the mass of the sun. And it turns out that the ranges of luminosity and temperature also correlate with mass. So those low mass stars are also very low luminosity, and the high mass stars are high luminosity. The low mass stars are low temperature or cool, and the high mass stars are high temperature or hot. The stars themselves over those ranges and properties have an enormous range in size, as we can see here on this continuously varying scale model that puts all the star sizes in reference to more familiar objects. So we can see that giant and supergiant stars are literally tens of thousands of times larger than the Sun. Incredible. They also are such high luminosity that they last a lot shorter lifetime than the Sun. So we can connect mass and lifetime. Think of the mass of a star as its fuel tank. It's using fuel in the fusion process, converting hydrogen to helium when it's on what's called the main sequence. The Sun's life expectancy is about 10 billion years, which means that with an age of 4.5 billion years, the Sun is about halfway through its life, continuing to fuse hydrogen into helium. It'll go on doing that with no visible change in its output for billions of years. But if we take a star 10 times more massive than the Sun, it would seem to have a 10 times bigger fuel tank. We might imagine that it would last longer than the Sun. But in fact, its luminosity is so high, that's the amount of energy it puts out per second, which is how fast it's using its fuel, and it's using its fuel 10,000 times as fast. So it actually lasts 10 divided by 10,000 times 10 billion, which is 10 million years. So a star 10 times the mass of the Sun actually lives in a blink of the eye compared to the Sun, 1,000 times less. What about a very low mass star? We might imagine it wouldn't last very long because its fuel tank is so small. The smallest mass star has a little over 8% of the mass of the Sun, say 10%. With 10 times less fuel, it, however, uses the fuel at 1% of the rate. And so it actually lasts 10 times longer than the Sun. That's 100 billion years. And so we have the bizarre attribute that the high mass stars are like gas-guzzling cars, big, heavy, with very inefficient engines that use their tank of fuel very quickly, whereas the low mass stars are like fuel-efficient, miserly cars that have small fuel tanks, but they're so efficient they go much further on their tank of gas. That's a good analogy for remembering this relationship, this inverse relationship between star mass and its lifetime. So, the general features of stars are that the high mass stars are high luminosity, putting out a lot of energy, they're short-lived, they're large radius, and they're hot, so they look blue to us in the sky. Whereas the low mass stars are low luminosity, less intrinsic energy, they have long lives, small radii, and they tend to be cooler or redder. And you can see here the Sun as a G2 star put in a spectrum that compares it to Sirius, a star with twice the Sun's mass, substantially hotter, Spica, which is a B giant and substantially more massive and shorter lifetime than the Sun, and then Proxima Centauri, which is a red dwarf, an M star, with a mass just about 10 times less than the Sun. There are also stars that are not on what we call the main sequence. The main sequence is that diagonal stripe across the HR diagram that denotes the stars converting hydrogen to helium in the first phase of their life, like the Sun. But on the HR diagram, astronomers found other stars with other combinations of property, and they deduced that these are giant and supergiant stars, massive stars near the end of their lives that are burning other nuclear fuels. They also found stars low on the HR diagram, so very low luminosity, but also extending to high temperatures. These small stars are either low mass stars that might be cool, like a red dwarf, or hot stellar embers, like a white dwarf. We'll talk about both of these. That's the end of this topic.